In this video, we're going to continue to explore performing mathematical computations with NumPy arrays. Now, I deviated a little bit from the text or flow of the notebook in the previous video, but if you read through on your own time, you'll see it basically works through the exact same examples that I previously discussed. But we can also perform a variety of calculations with arrays that go beyond just performing sums. Often we will want to transform our data by scaling it or shifting it, performing what are known as linear transformations. So we could have, for instance, an array of the numbers 1 through 5. And if we wanted to shift those all to the right by 5 units on the real number line, we could just take our array A and add 5. So this kind of syntax would certainly not work with lists. I cannot say, for instance, 1, 2, 3, 4, 5 plus 5. That doesn't work. But with an array, it's not a problem. Because again, NumPy is expecting us to treat arrays for the most part as mathematical objects. Particularly if since arrays have a data type and we know that every element is an integer or a float or a bool, there's a straightforward interpretation of addition by 5 for every element in this array. And NumPy knows that in advance because of the array's data type. So we can add 5 to every element, multiply every element by some value, or divide every element by some value. And in this last example, it even resulted in our in the output having a data type of float rather than integer. So we had an array that has a data type integer. Since everything, you can check it yourself, everything in here is an integer. And if you construct an array like this, you can check that the d type is integer. But when we divided by 5, the result was an array with data type float. And we can use this power to define new arrays relative to old ones based on mathematical operations, just like we might do for individual integers or floats. And we can also add together arrays or multiply them together or divide them element-wise. And if you're accustomed to thinking about these sorts of objects, these like matrix-like or tensor-like objects as linear algebra objects, it is important to note that the default interpretation of these mathematical elements or operations is to perform them element-wise. So when we multiply together two arrays, they are multiplied together element-wise. They are not combined using matrix multiplication or by an inner product or any of those linear algebra operations. It is an element-wise operation. It is possible to perform linear algebra. We can take inner or outer products between arrays. So we have two arrays now, A and B, both 5 elements long, one-dimensional. So these resemble, for instance, vectors in linear algebra. We could take a dot product of these two vectors. You would get 1 times 2 plus 2 times 3 plus 3 times 4, etc. Or we could take an outer product of these and end up with an array where we have 1 times 2, 1 times 3, 1 times 4, 1 times 5, 1 times 6, 2 times 2, 2 times 3, 2 times 4, so on. So for the inner product, it turns out the inner product of A and B is 70. So inner products always return a single number. We take every component, multiply them against each other, and then add up all those products. The outer product, we multiply every possible pair of components and end up with a matrix as output. I'm going to skip ahead a bit since we've already talked about a lot of this. I'm also going to skip this universal functions section for the most part, but the idea is essentially that just like we can, when we add 5 to every element in the array, essentially that plus 5 is being broadcast over the array. The entire array is receiving this plus 5 operation. And likewise, for things like sine and cosine or logarithm, those functions get broadcast over the array, and that takes advantage again of the highly optimized C code that NumPy arrays are based on to perform those calculations very quickly. I'm going to jump down to this basic data aggregation, and we'll wrap up discussing arrays with a little bit on reshaping and combining arrays. So we've done a few data transformations now, just adding and multiplying together arrays with numbers or other arrays, where each element of the array was mapped to a new element. A transformation is a one-to-one operation, meaning for each input I get an output. We're now going to talk about aggregating data in NumPy, which is a many-to-one operation, meaning for several inputs I get one output or fewer outputs. So, for example, when we calculate a statistic like a mean or a variance, that is a data aggregation because we are taking a collection of numbers and summarizing them with one or a few numbers. We'll be talking a lot more in data aggregation in the coming lectures. So, to show off the data aggregation abilities of NumPy, we're going to use, first of all, the random submodule to create some fake data. The random submodule has a lot of different functions for generating random numbers according to a variety of distributions. We can generate random integers, which we'll do in a moment. We can generate random values from the interval 0 to 1, just uniformly distributed between 0 and 1, and then we could scale those by multiplication if we wanted. We can generate random numbers from a standard normal distribution, and there are a variety of other probability distributions that I'm not going to describe at this time that we can use for generating random numbers. And we can also perform random sampling from a pre-existing collection of numbers if we have some measurements, for instance. In this case, the fake data we're going to generate is supposed to be represented of sales at a cafe, how many cups of coffee we've sold. And we can only sell integer amounts of coffee, integer cups of coffee. We can't sell half a cup of coffee. So we're going to go ahead and generate random integers for each day in January, where we imagine we sell between 25 and 200 cups of coffee. And for the ease of this example, we're going to pretend that January has 4 weeks, each consisting of 7 days. Now, of course, January has 31 days, not 28, but for the sake of our example, we're just going to say we're interested in 4 weeks that approximately line up with January. So we have Sunday, Monday, Tuesday, Wednesday, etc. for weeks 1 through 4. And we might want to take these sales figures and compute various statistics describing how sales went for particular days of the week, or during the month, or during a particular week. So we might want to see, for instance, the sale totals for each week, or the average sales for Monday. So we can calculate means, for instance, using the mean method of a NumPy array. So the mean number of coffees sold in January is simply the array dot mean. So on average, we sold 110 cups each day. If we wanted to see the mean sales on Monday, we could slice the array and then calculate a mean. Slicing works similarly as it does in lists, except instead of having hierarchical indices for each layer in the list, we have a sequence of indices indicating the different dimensions of the array. So for instance, this is a two-dimensional array, right? Rows and columns. We could get the first row by asking for row 0 and from beginning to end of the columns. So this is our first row, row 0, all the columns, beginning to end. We could get row 1. We could also slice maybe everything but the weekend. So if Sunday is here and Saturday is here, we could slice from 1 to -2, or -1 actually. And that gives us the weekdays, Monday through Friday. And of course, we could select all the Mondays by taking every row and the first column, or column 1, second column. So we get 117, 99, 174, 45. So by slicing the array in this way and then calculating the mean, we'll get just the mean for the sales figures from Mondays of January. So on Monday, we sold an average of 108 cups. We can also do things like ask, when did we have the most sales? So we know in Python we can find the maximal element of a list or other data structure by using the built-in max method. But if we wanted to know where that element was found, we would have to do something more complicated. So for instance, if I had, well, let's look at how it goes in NumPy first, and then we'll talk about how to do it in built-in Python. So in NumPy, there is, first of all, a max function. So the maximum number of coffees we sold in January was 185. But there's also an argmax. which tells us the index at which the maximum occurred, 23. So since we number our days starting at 1 and not 0, the day with the maximal sales is that argmax plus 1. So January 24th was the day with the highest sales. Now we could also do this in raw Python. So here's a list containing all of our sales. I could get the max of that list, 185, just as we expected. And I'll actually take this out and say Jan coffee sales list is this. So max Jan coffee sales list. And if we wanted to know where that occurred, we would have to say, okay, January coffee sales list, what is the index of this element? 23rd. Okay, same as we got out of argmax. But we can see there's this line of code is quite a bit longer. We have to calculate the maximum and then go looking for it in the list. And additionally, it's just a lot more code, a little bit harder to understand, a little less elegant. We can also do more complex calculations. For instance, maybe we're interested in if there is periodicity throughout the week. Do our sales rise during the weekend? Is there a natural rhythm to the sales as the days go by in the week? You know, we might imagine that we sell more coffee on the weekend. Or maybe we sell the most coffee on Mondays because, you know, everyone is waking up on Monday to go to work, and they got used to sleeping in on the weekend, and now they have to get up bright and early on Monday. Could be anything. Of course, we wouldn't expect to find any pattern in this case because our numbers are just randomly generated, but this is just an illustration of something we could imagine doing. So I'm not going to walk through every step of this calculation. You can see at a glance it's a little bit complicated. And you can learn more about studying time series of data for periodicity in Unit 2 of the data science module. But here we're just subtracting off the mean of the coffee sales, so we get our sales relative to the mean, plus or minus, and then scaling them so that they fall between -1 and 1. And then we perform what's called a Fourier transform to calculate the power spectrum of our sales. And these fractions are telling us the frequencies of how should I explain this? What we're seeing here is a distribution of kind of the amount of signal, the amount of the pattern of our sales distributed across various frequencies. So the frequencies are here on the left. Once every 28 days, once every 14 days, every 2 weeks essentially, once a week, all the way up to every other day. So we have a bunch of different periodicities here, and the amount of signal that belongs to each one. So for instance, if we were interested if there's a weekly rhythm, we would be interested in this once per 7 days frequency. And we can see there's more power here than in some of the other frequencies, but for instance, 1 every 4 days, 1 every 4 days has even more power. And in truth, this is all really just noise, right? Because our data was just randomly generated. So nothing really jumps out very large above all the others. We would be looking for something that was 1 or 2 orders of magnitude larger than the other components at least. But though this code looks quite a bit complicated, most of that complication comes out of things like unfamiliar functions that we're calling. But just looking at the form, it's relatively simple. In very few lines of code, we're able to calculate these frequency components. And at least one of these lines is actually mostly dedicated to just formatting these frequency components as fractions. So that shows off some of the data aggregation abilities of NumPy. We're going to continue to build on these abilities as we discuss pandas and learn not only how to, for instance, slice along different dimensions of our data or select different parts of our data for aggregation, but also learn how to group our data based on the values themselves. I want to talk about 2 more topics before wrapping up. One is related to this idea of slicing before aggregating, and that is that in NumPy we can filter our data based on the values themselves. So for instance, say I had an array and we'll just take well, I could do this with a range. Why don't we do that? The numbers between 0 and 9. And if I wanted to get out the numbers that are even, one way I could do that is to simply notice that, I start at 0. So I could just count by 2s, no? Let's see here. There we go. So I just count by 2s, and that's fine, but I don't necessarily know what the values will be in advance. What if I had just random integers, and I had 100 of them? How would I get the even ones now? They're in no particular order. Well, I could iterate through and that's fine, but it's a little bit verbose. And I have to iterate through this array. Is there a better way? It turns out there is. So if I have a bunch of random integers, and I want to get the even ones, I can slice them according to a condition. So let's call this random array. And if I want the even elements, I can take my condition and simply use that to slice the array itself. So here I get only even numbers. What's going on here is when I perform this Boolean transformation, this is a Boolean operation. So just like we could do +5 to the array, we can also do Boolean operations. And when we do that, we transform our array into a Boolean array based on whatever computation we did. And then we can use this to slice our array, or any other array of the same shape, and pick out only the elements that are true. This is a very useful tool. This is sometimes called like filtering by condition or conditional filtering. And we'll see this come back in pandas as well. But the pandas functionality originates here in NumPy. It's worth noting, for instance, we could also say, take our random array, and another way we could slice this up is, we see 1, 2, 4, 5, 6. These are all true. So I could also do 1, 2, 4, 5, 6, and get out those elements just by passing in a list of the indices that we want to slice out. So that's also an option. A little less powerful than this conditional slicing, but again, is a new functionality compared to slicing lists. With lists, we could not, as far as I know, do something like this. List range 10. Yeah, so we couldn't do something like that with lists. We'd be told list indices must be integers or slices, not a list. Yeah, there's simply no way to pick out a collection of individual elements, as far as I know or remember, from a list. We would instead have to come up with like some way of expressing this as a slice, which for something like this is not so hard, right? That would just be 1 through 3, or 1 through 4. But for some, if we wanted to get 1, 2, 4, 5, 6, it would not be very easy to express that in the typical slicing syntax for lists. All right, I'm going to cut the video here. We'll do one more video on NumPy, actually. This is running a little long, so in the next video, we'll talk about the very last topics, which is manipulating the shape of arrays and combining them together.